global warming isn't some distant threat anymore, is it? It has reached some seriously critical dimensions.
It absolutely has. And the
Yeah.
main drivers, the things creating the most trouble, are heavy industry.
Right. Think iron, steel, cement.
And of course, those massive fossil fuel power plants we already have running.
So if we're going to navigate this whole decarbonization process and, achieve competitive, sustainable development, we have to deploy some pretty sophisticated new tech right now.
That's the challenge. And today, we're diving deep into what is arguably one of the most essential tools we have for managing those existing emissions. Carbon capture, utilization, and storage.
CCUS.
Exactly.
Yeah.
The research we're looking at positions CCUS as a critical technology, especially in near to medium term. It's a necessary bridge to get us to net zero
The
emission.
bridge, I like that.
Our mission today is really to analyze the cutting edge of that research, focusing on how to optimize the entire CCUS supply chain.
So not just capture, but the whole journey.
The whole thing. How we capture it, how we move it, and critically, how we put it to use to meet some really ambitious goals, like the 2053 Green Development Goal.
Okay, let's unpack this then. We're talking about massive, decades-long infrastructure projects here, and they're all driven by policy. So what's the global backdrop that created all this urgency?
Well, it really started with foundational international efforts. You can stretch it all the way back to the Kyoto Protocol, signed in '97.
Sure, but the real game changer was the Paris Agreement, wasn't it?
That was it. That's what set the current long-term goal for pretty much every nation on Earth, limiting the global temperature rise to well below 2 degrees Celsius.
And striving for that 1.5-degree mark, that's the number that keeps coming up.
It is, because the scientific consensus is that staying below that threshold really reduces the most catastrophic climate risks. And this policy, it doesn't just exist on paper.
It needs economic teeth.
Exactly. Like the massive European Green Deal from back in December 2019. That's a key driver, pushing for zero net greenhouse gas emissions by 2050.
And when we say greenhouse gas, or GHG, just for everyone listening, we mostly mean CO2, but also methane and a few others that trap heat.
Correct. And to get those emissions down, governments rely on mechanisms that basically make polluting expensive.
Carbon pricing.
Carbon pricing. These are crucial tools to incentivize GHG reduction. And we see two main ways they do it globally.
The two main flavors of economic pressure.
Right. The first is the emission trading system, or ETS. It works by setting a cap on the total amount of emissions allowed in certain industries.
So if you're a clean company, you can make some money.
Precisely. Companies that emit less than their cap can sell their remaining allowances to companies that emit more. So you get this variable market-based price for carbon.
Okay, and the second method?
That's the carbon tax. Much simpler. It just defines a tax rate applied directly to GHG emissions or the carbon content of fossil fuels.
So the price is fixed, not floating like in the ETS.
Exactly. But both systems are designed to do one thing: push emitters toward expensive solutions, like CCUS.
Okay, that sets the global stage. Let's zoom in now on the specific challenge facing the region in the source material. We're talking about a national economy that ratified the Paris Agreement pretty recently, October 2021.
Yes, and they're grappling with massive growth at the same time. If you look at their 2019 emissions, the total was huge: 506.1 million tons of CO2 equivalent.
Wow. And where is most of that coming from?
It's overwhelmingly concentrated in one area. Data from 1990 to 2019 shows that energy sources accounted for 72% of total emissions.
72%. And agriculture was a distant second.
Very distant, at about 13.4%. The problem is the power sector.
And here's the real tension, right? The thing that makes CCUS so non-negotiable for this region. They're committed to decarbonization, but their energy demand for electricity, coal, oil...
It's increased the fastest in this specific region across all of Europe in the last decade.
So their 2020 energy mix was still heavily reliant on coal and gas.
Very. Coal at nearly 35% and natural gas at over 22%. They just need the energy now.
And it's not like that's going away. The sources say they're actually building new coal plants.
That's the critical point.
Yeah.
As of January 2021, almost 30%, 29.6% to be exact, of all planned new installed capacity belongs to coal power plants.
So a complete, immediate abandonment of fossil fuels just isn't economically or strategically feasible for them.
Which raises the fundamental question: how do you reconcile a necessary commitment to net zero goals with the reality of ongoing fossil fuel construction?
And the only plausible answer has to be technology.
Specifically, CCUS. It's the essential tool for managing emissions from sources that you just can't easily transition to clean energy yet.
That brings us to the tech itself. Now, we often hear about CCS capture and storage, but we're focusing on CCUS. Why the extra U for utilization? Why is that one letter such a difference maker?
Because CCS alone is an extremely high-cost technology. I mean, you capture the carbon, and then you pay to bury it indefinitely.
It's all cost, no revenue.
Exactly. Adding utilization is crucial because converting a portion of that captured carbon for productive use completely changes the economic calculation. It lowers the costs.
In some cases, it can even create a revenue stream.
It can. It makes the whole thing much more economically viable and scalable.
And this isn't science fiction. This is happening now on a global scale.
Not at all. There are about 35 commercial CCUS facilities operating globally right now, capturing nearly 45 million tons of CO2 every year.
That's incredible.
Even more so, the International Energy Agency reports that integrating CCUS can reduce the overall cost of fighting the climate crisis by an astounding 70%.
70%? Wow. That really underscores why utilization matters. Because heavy industry, things like cement, steel, fertilizer.
They are incredibly difficult and expensive, sometimes impossible, to just electrify or switch to hydrogen. They need a different strategy.
And the CCUS value chain provides that strategy.
It absolutely does.
This is where it gets really interesting for me. Let's break down the journey of that carbon molecule. It starts with capture. What are the main ways we pull CO2 out of an industrial stream?
There are three main approaches. The most common is post-combustion capture. It's exactly what it sounds like.
Yeah.
You grab the CO2 from the flue gas after the fuel has been burned.
Like scrubbing the exhaust fumes.
Pretty much. Then you have pre-combustion. This is where you gasify coal or reform natural gas to produce a mixture, often CO2 plus clean hydrogen, before you burn it. You capture the CO2 from that mix.
And the third?
Oxy-fuel combustion. You burn the fuel in almost pure oxygen instead of air. That gives you a much more concentrated stream of CO2 and water, which makes the capture part a lot simpler.
Okay, so once the CO2 is captured, it has to move. What are the transport options?
Pipelines are the main method for big, continuous volumes, but you also have specialized ship tankers, or for smaller amounts, even land transport like road tankers or trains.
And then the final destination, storage. Where do you put all this carbon?
4 primary geological spots. First, deep underground saline formations. Think of them as layers of rock filled with salty water.
Okay.
Second, unleanable coal seams. Third, old depleted oil and gas fields. And fourth, enhanced oil recovery, or EOR.
Let's pause on EOR because that's the bridge between storage and utilization, right? What is actually happening there?
Right. It's highly effective, and it provides that revenue stream we were talking about. You inject pressurized CO2 deep into a mature oil reservoir.
So the CO2 pushes more oil out.
It acts like a solvent and a pressure agent. It mixes with the remaining oil, makes it flow better, and repressurizes the reservoir, pushing out oil you couldn't otherwise get.
So it's a utilization method because it helps production.
And it's a storage method because a huge chunk of that CO2 stays trapped underground permanently.
Okay, so beyond EOR, where else is this captured carbon being used? Because the future can't just rely on oil markets.
It can't. And the list is surprisingly diverse. It's used heavily in food processing.
Like carbonating drinks.
That, and even decaffeinating coffee, according to our sources. It's also essential in making chemicals like methanol and urea, which is a major fertilizer component.
And even steel manufacturing and mining.
Yes, and even in niche applications like cooling explosives in mines. This is what turns a simple cost into a real value chain.
But that transformation is all about optimization. The challenge isn't just if we can do it, but how we design these incredibly complex systems efficiently.
It is. The research highlights that designing an optimal CCUS supply chain network requires making 9 key decisions all at once. It's a massive logistics puzzle.
9 decisions. Okay, let's slow down here. Can you lay out those 9 critical variables that these models have to juggle?
Sure, we can group them. First are the capture decisions. How much CO2 to capture, which sources to capture from, and which capture technology to use at each site.
Okay, that makes sense.
Second, the transport decisions. Where to construct the pipelines, and critically, what diameter those pipelines should be.
Hold on, pipeline diameter. That sounds like such a small detail. Why is that a major optimization problem?
Because it's the heart of the cost calculation. A bigger pipe costs a lot more upfront to buy and to lay, but it lets you move more CO2 with less energy over the long run.
So you have to balance that huge initial cost against decades of operational savings.
Precisely. Third, the storage decisions. The model has to decide which reservoirs to use for storage and how much CO2 to inject into each one.
And the last two?
They're about the overall network, how the distribution network should be structured between the sources and the reservoirs, and finally, which utilization areas to prioritize.
And the models that solve this, you called them mixed integer linear programming, or MILP. Can you explain what that actually does in simple terms?
It's the perfect tool for this problem.
Mm.
The integer part handles the yes-no decisions. Do we build a pipeline here? Yes or no? The linear programming part handles the continuous choices. How large should the pipe be?
So it combines the big if questions with the how much questions.
Exactly. It integrates all 9 decisions to find the route with the lowest cost and the highest carbon reduction, all at the same time.
And what does running these massive models tell us about the trade-off between just burying the CO2 versus using it?
The models are crystal clear. Utilization is a huge economic driver. Studies show that CCU is decisively preferred over pure CCS if there's enough demand in the enhanced oil recovery market.
So the economic incentive from EOR is what makes the whole environmental solution financially attractive.
In many cases, yes. That's what makes it scalable.
But that raises a critical point. We're talking about solving a climate problem with profits from boosting oil production. Isn't that a paradox?
It is an operational paradox, absolutely.
Yeah.
The models just report on the financial reality. For a lot of growing economies, that EOR revenue is the vital early-stage capital you need to build the bigger network, the pipelines and compressors.
The infrastructure that you'll need later for pure geological storage.
Exactly. The initial financial benefit subsidizes the necessary climate infrastructure.
That makes sense from a practical standpoint, but optimization can't just be about money and tons of CO2.
You're right, and the models are expanding. Recent research emphasizes multi-objective optimization. So now they include not just financial costs, but also things like environmental impact, societal risk.
Like pipeline safety and community acceptance?
Yes,
Yeah.
and broader socioeconomic factors like job creation. It has to be a holistic design.
Which leads perfectly to the path forward. The research identified a gap, the need for these fully integrated multi-region models that optimize all these goals at once.
That gap has to be filled. And to do that, the research proposes 5 specific integrated recommendations to build a truly robust national network.
Okay, so let's review that blueprint. What's the first key element?
First, you have to expand the storage options. The current focus is too narrow. The models need to include all geologically suitable areas, like the Batman-Badaraman oil field, the Sirte-Dodan field, even spots in the Mediterranean, and the Salt Lake region.
You have to map every single potential trap.
You do. Second is greater source and technology variety. Include all the high-emission sources, like those new power plants, and every type of capture technology we talked about.
And you can't assume it'll all move through pipelines.
That's the third point. Transport flexibility. The model has to integrate pipelines, sea transport, and road or rail to find the most cost-effective solution dynamically.
And of course, getting back to the U.
The fourth point, utilization diversity. You have to model a network that goes beyond just EOR to include chemical production and food processing. That makes the whole system resilient if oil prices fluctuate.
And the final point.
Risk inclusion. The models must intentionally include and minimize various risks, environmental, societal, socioeconomic, to make sure you have public buy-in and true sustainability.
This sounds like the playbook for how you build a carbon infrastructure system that actually lasts for 50 years.
And that's the key to achieving sustainable green development while meeting energy demands. Implementing these suggestions could make CCUS both effective and, crucially, affordable.
This has been a fascinating deep dive. We've established CCUS as a non-negotiable tool for the near and medium term. We've explored the tech, and we've highlighted this incredibly complex 9-variable optimization required to deploy it.
And we've really seen how optimization turns what would be a tremendously expensive climate solution, just basic CCS, into a profitable, scalable system once you include utilization and all those other factors.
Indeed. Now, for a final provocative thought for you to chew on. Considering those 9 key decisions needed to optimize a CCUS supply chain from pipeline diameter to reservoir choice, which single factor do you think is the greatest practical hurdle to rapid CCUS deployment today? Is it the raw economic cost, the regulatory risk of policies changing, or the geological uncertainty of just finding enough good storage? Something to mull over until next time.